Okay, this lesson is on the intersection of two planes, and we're going to learn how to predict how two planes will interact in space by analyzing their normals and learning to find the equation of the line of intersection of two planes. It's important here. That intersect in a line. So if we try to envision the way two planes can interact in space, we kind of have two categories related to analyzing their normals. So if their normals are scalar multiples, so in other words, if n2 is some multiple of n1, but the constant is not in that same scalar multiple, then you have two planes that are parallel and distinct, okay? However, if the normals are scalar multiples and the constants are in that same proportion, those are true, then you have two planes that are coincident. We also say that the intersection is a plane. Or a pi, pi is short for plane of intersection, pi OI. Okay, so the two planes are coincident. There's a plane of intersection. In the case where they're parallel and distinct, there's no intersection. And then we have the one where, this is what we're going to spend most of our time learning about today, is when the two normals are not scalar multiples of each other. So if that's true, the normals are not scalar multiples of each other, then you automatically have a line of intersection. And we're going to learn how to find the equation of that line of intersection. But you can see here's the lighter pink plane and the darker pink plane, and they're not parallel. And then here is our line of intersection, LOI, line of intersection. Okay? And so we analyze the normals. If they're not scalar multiples, not scalar multiples, then you automatically have a line of intersection. If they are scalar multiples, then you check the D values to decide whether there's no intersection and the planes are parallel and distinct, or whether there's a plane of intersection and the planes are actually coincident. So if the normals are not scalar multiples, you have a line of intersection, and we're going to learn how to find the equation of that right now. So find the intersection of these two planes here. And I've done a little diagram here, but I'm also going to kind of go through my analysis with you here. These should have vector symbols over top, but I snipped this picture from the internet. So it's showing, here's this semicircle here represents a plane kind of looking, I'd say, vertically up and down, and its normal is N2. Sorry, its normal is N2. And then this plane here is flat, and its normal 1 is going up and down. So up and down. And then this line here is the line of intersection. And I'm going to convince you that the direction of that line of intersection is the cross product of the normals. Okay, so I've set up a model, and we'll just talk about why that's true here. So I'm going to change my camera view here. So here's my two planes. So this is my first plane, and this is my second plane. And the red pen's going to represent a normal, so it's perpendicular to this first plane here. And the green pen is representing a normal of the second plane. So you can see they're both perpendicular to the planes. Now, if I do the cross product of the red and the green, I'm going to get a vector that is perpendicular, a direction that is perpendicular to both the red and green, or the two normals of the planes. And if you can see that yellow pen sticking out there, I don't have a third hand to hold it, it's perpendicular to both red and green. And I'm just going to hold it up so you can see that. So straight out is perpendicular to red. Then if I let the red one go, this direction of the line of intersection is also perpendicular to green, and that represents this line along the two planes. So here's the line of intersection here, I'm showing you, and its direction is this direction here. So if I find the cross product of the normals, that's going to be the direction of the line of intersection. And to get the equation of a line, I need the direction and I need a known point. Those are the two things that I need. So we know we can find the direction vector by finding the cross product of the normals. And then I'm going to show you how we can use elimination and also left side, right side checks to find a point that the planes share. Okay, I'm just going to go back to my picture here again for a second. So we want to find, if we find a point that is on this plane here and on this plane here, then it's got to be on the line of intersection. So a point that is on both the plane that has the red normal and the plane that has the green normal has to be along this line of intersection. We call it a shared point. If it's on both planes, then it's a shared point and it has to be along that line of intersection. Okay? So it has to satisfy the equation of both planes. All right, so first thing, we're told here to find the intersection of the planes if it exists. So the first thing we would do if we didn't already have this diagram indicating to us there's probably going to be a line of intersection is we would look at the normals. So the normal of the first plane is 3, 4, 0. Be careful, there's no Z here. Okay, and the normal of the second plane is 1, 2, 3. Okay, and it's easy to see that they're not scalar multiples, so I'd start off by making that statement. N2 does not equal a scalar multiple of N1, so therefore right away we already know there's going to be a line of intersection. It's up to us now to find that line of intersection. So the first thing I want to find is the direction of the line of intersection. So I'm going to find the cross product of the normals. So and I can do that on a scrap piece of paper. So here's my first normal, 3, 4, 0, repeat the 3, and my second one below it. So my normal is going to be 12 minus 0, or sorry, my direction vectors. The first component is 12 minus 0. Second component is going to be 0 minus 9. Which is negative 9. And the third component is going to be 6 minus 4, which is 2. Okay, so that doesn't have a nicer scalar multiple, so that's going to be the direction of our line. So that's going to be the direction vector M of our line of intersection. So the first thing we do is find the direction of the line, and the second thing we do is we find a shared point, so a point that is on both of the planes. And to do that, we use elimination, and because we have 3 variables and only 2 equations, we have to do a little guess here. So what I usually do is I let z equal 0, because in many cases there will be a shared point that both of them have a z value of 0. If you get an inconsistent system, which will happen sometimes, then you scrap letting z equal 0 and you let y equal 0. Okay, and then chances are you'll find a shared point along an infinite line that has a y value of 0. And if that didn't work, then your last resort would be let x equal 0. So if I let z equal 0 in these 2 equations, the first one's not going to change, so I have 3x plus 4y minus 5 equals 0. And if I let z equal 0, my second equation would become x plus 2y minus 3 equals 0. So if I let z equal 0 3 times, z would be 0 as well. Now I want to make these equations look more like they did when we used elimination to solve a system in grade 10. So here's my equation 1 and my equation 2. And by looking at them, I can see if I were to multiply the second equation by 2, I would get a 4y here. And so I'd have a 4y here and a 4y here, so I could eliminate y. So to eliminate y, this is what I'm going to do. So I'm going to keep the first equation the same-ish, but I am going to add 5 to both sides. So I've got my variables on one side and my constant on the other. So that's equation 1, and all I did was rearrange it. But equation 2, I'm actually going to multiply everything by 2 in it, so I get that 4y that I want. So I have to multiply the x by 2, the 2y by 2, and the negative 3 by 2, which is going to give me negative 6, but I want it on the other side, so it's going to be positive 6 on this side. And then I'm going to subtract to eliminate the y's. I'm eliminating y here. So 3x minus 2x is x, 4y minus 4y is 0, 5 minus 6 is negative 1. Okay, so now I'm saying z is 0 and x is negative 1. I want to find y. I want to find the y that goes with z being 0 and x being negative 1. I can use either of these equations to find it. So I'm going to find y now. Maybe I'll use 2 here. So x we said was negative 1 plus 2y minus 3 equals 0. That's going to give me 2y equal to positive 4 or y equal to 2. So I'm saying that, so my point is going to be made up of an x value of negative 1, a y value of 2, and a z value of 0. And we want to know, is that a shared point or not? So just we want to check it is actually on both planes. Check it is on both planes. So I'm going to do a left side, right side check. So here's pi 1, my first plane. So I'm checking x being negative 1, y being 2, z being 0, and seeing if my left side and right side equal. So 3x plus 4y minus 5 on the left, 0 on the right. And I'm going to replace x with negative 1, so that's going to give me negative 3 plus 4 times 2 is 8 minus 5 gives me 0. So since the left side equals the right side, p negative 1, so the point negative 1, 2, 0 is on the first plane, pi 1. And then I'm going to do the second plane. I'm going to run out of room here, but I'm going to do it. Some people do it, they do the check in their head, okay? Check and make sure this point satisfies this plane by thinking negative 1 plus 4 is 3 plus 0 minus 3 is 0, okay? But I'm going to write it out because it's the first time that we are doing this. So I'm checking x to be negative 1, y to be 2, z to be 0, and that does give us 0, which means that therefore p is on pi 2 as well. So that means it is a shared point. So this is a point that's on both planes, which means it has to be on the line of intersection. So this point is on the line of intersection because it's on both planes. And then this is the direction of the line of intersection. And if we put those things together, therefore the line of intersection is R, and usually they want the vector equations. So if they ask specifically for parametrics or symmetrics, you can accommodate that. So R is going to be negative 1, 2, 0 plus t times our direction vector, 12, negative 9, 2. So that's how you find the line of intersection of two planes. So first we figure out that the normals are not scalar multiples, so we know we have a line of intersection. To get the direction of that line of intersection, you take the cross product of the normals. Then you have to use elimination to find a shared point. We start off letting z equal 0 and see if we can solve for x and y. Then we check and make sure that point is on the two planes, either mentally or writing it out. or writing it out on scrap paper. Once we're satisfied that point is on both planes, then we have our point that's on both planes, we have our direction, and we can make our statement with the line of intersection. Okay, question 2. Find the intersection of the two planes if it exists. So again, we're going to start off looking at our two normals. So the normal of this first plane is 2, -2, 5. And the normal of the second plane is 2, 1, -4. And I can already see they're not scalar multiples, so I'm going to say n2 is not a multiple of n1, is not equal to kn1. Therefore, we know there's a line of intersection. So immediately, I'm going to find the cross product of the normals because that's going to give me the direction vector. So I'm going to do that on scrap paper so I don't run out of room here. So 2, -2, 5, repeat the 2, 2, 1, -4, repeat the 2. Start here. So that's going to be 8 minus 5. 10 minus -8, which is 10 plus 8, and 2 minus -4, which is going to give us 3, 18, 6, which can be reduced. So our direction vector is going to be the vector m equals, so if we divide each component by 3, 1, 6, 2. So now we want to find a shared point. So if I look at my two planes, I'm going to let z equal 0, and then write my two planes. So my first plane I'm going to write as 2x minus 2y. If z is 0, the 5z term's gone, and I'm going to subtract the constant over to the other side. And then here I'm going to have 2x plus y, -4 times 0, the z's gone, and then subtract the 7 over to the other side. And I can eliminate x now just by subtracting. So here's my equation 1 and equation 2 with z equal to 0 in them. I'm going to subtract, which will eliminate x. So 2x minus 2x is 0. -2y minus y is -3y. -10 minus -7 is -3. So we're going to get y equal to 1. So far we have y is 1 and z is 0. We need to find x. So I'm going to use this equation again. So 2x plus y, which is 1, equals -7. 2x equals -8. So we get x equal to -4. So we're saying that our shared point, so is the shared point, we think, -4 for x, 1 for y, 0 for z on both planes. So we can check that. So we can check that it's true for the first plane, pi 1 here. So the left side we have 2x minus 2y plus 5z plus 10, and on the right side we have 0. And we're checking the point x is -4, y is 1, z is 0. So that's going to give me 2 times -4 minus 2 times 1 plus 5 times 0 is 0 plus 10. So it does equal 0. So since left side equals right side, p is on pi 1. Same thing for pi 2. So the left side of the second plane is 2x plus y minus 4z plus 7. And the right side is 0. So it's going to be 2 times -4 plus 1 minus 0 plus 7, which gives me 0 again. So that means therefore, since the left side equals the right side, P is also on pi 2. If it's on both planes, then it's a shared point. So now we know that this is a point on the line of intersection. This is the direction of the line of intersection. So therefore, the line of intersection, LOI, is R equals -4, 1, 0 plus T times 1, 6, 2. Okay, question 3. Find the intersection of the two planes if it exists. So first we're going to look at the normals. The first normal of the first plane is 3, -1, 4. And the normal of the second plane is 6, -2, 8. And those are scalar multiples. So I can see that n2 is equal to 2n1. So now I test. Is d2 equal to 2d1? So if that were true, d2 is 3. Is 3 equal to 2 times -2? No. Okay, so that's not true. So therefore, there is no intersection. The planes are parallel and distinct. Okay. So the normals, there are scalar multiples, which means they're either parallel and distinct or coincident. Then you're going to test the d values. d2 is not equal to 2d1, so that means they're not coincident. They're parallel and distinct. So there's no intersection. So if it says find the intersection, you're going to say there is no intersection. Question 4, find the parametric equations of the line of intersection of the planes if it exists. So we'll look at the normals. Remember it says parametric here, so sometimes you can forget little subtle things like that by the time you're at the end of the question. And one is 3, -1, 4. And our second normal is 1, 1, -2. And I can see they're not scalar multiples, so it does not equal a scalar multiple of n1. So therefore we know there's a line of intersection. So if we want its direction, we're going to find the cross product of the normals. So I'll do that on scrap paper. So 3, -1, 4, repeat the 3, 1, 1, -2, repeat the 1. So we're going to have 2 minus 4, 4 minus -6, and 3 minus -1, which is going to give us -2, 10, 4. And so I want my direction to be m vector, and I'm going to divide each component by -2. So I'm going to make this +1, -5, +2 is my direction vector. And now I have to find a shared point. So a point that's on both planes is on the line of intersection. So I'm going to let z equal 0 again. So if z is 0 in this first equation, it's going to become 3x minus y equals 7. And if z is equal to 0 in the second one, I'll get x plus y equals -5. And I can see just by adding, I'm going to eliminate the y's. So if I add these equations together, because I have -y and +y, I'm going to eliminate y. So that's going to give me 4x equals 7 plus negative 5 is 2. So x is a half, which isn't horrible, but it's not awesome either, but we'll go with it. So now we have to find y. So I'm going to use the second equation. So x plus y equals negative 5. X is a half. So I'm going to subtract a half. And y is going to end up being negative 11 over 2. So we have to test then, is the point 1/2 for x, negative 11 over 2 for y, 0 for z on both planes. And it's a point in space, it's a fixed point, it's not a direction, so I can't find a scalar multiple of it, which sometimes people do accidentally. They're not thinking about it properly. So this is a little bit harder to test here. I want to make sure that I do this correctly. So my left side is 3x minus y plus 4z minus 7, and my right side is 0 for pi 1 here. So 3 times a half minus negative 11 over 2 plus 4 times 0 minus 7. So that's going to be 3 halves plus 11 halves, because minus and negative is add. And then if I make negative 7 out of 2, it's going to be minus 14 halves. And that is 3 plus 11 is 14, minus 14 is 0 halves, which is 0. So therefore, left side equals right side. Therefore, that point is on pi 1. So now we're going to see if it's also on the second plane. So my second plane is x plus y minus 2z, x plus y minus 2z plus 5 equals 0. So x is a half minus 11 over 2 minus 0 plus 5. So a half minus 11 over 2 plus, I can change 5 over 1 to 10 over 2. That does give me 0 again, because that's going to be negative 10 plus 10, so 0 over 2 is 0. So therefore P is, therefore left side equals right side, therefore P is on pi 2. So we know that this is a shared point, it is on both planes. And we know this is our direction. So I'll just fit my therefore statement in here. So therefore LOI is R equals a half negative 11 over 2, 0, plus T, 1, negative 5, 2. So it's okay to have fractions in your point. Perhaps if we'd let y equals 0 or x equals 0, we would have gotten a nicer point. But as long as you can go ahead and do the fractions and prove to yourself that the point is on both planes, then you're good. Okay, question 5. Find the intersection of the planes if it exists. So look at the normals. The normal of the first plane is 1, 1, negative 3. And the normal of the second plane is 3, 3, negative 9. So I can see that n2 is equal to 3n1, which means we either have parallel and distinct or coincident planes. So the normals are scalar multiples. Now we test, is D2 equal to 3D1? So D2 is negative 18. Is that equal to 3 times D1? Remember that if we want this to look the same, we would subtract the 6 over here, so D1 would actually be negative 6. That is true. So that's true. Okay, so that means therefore the planes are coincident. That's what it means geometrically, but it asks for the intersection. So therefore, the plane of intersection, pi OI, is, and then I would choose probably the reduced form, but you could choose either, saying either that or that is the intersection, because they're actually the same plane, just written differently. And that brought me to, if I go back to this last question here, it asked for the parametric equations, and I forgot about that. So parametrics are, so careful here, I'm going to put them side by side. So x equals a half plus t, y equals negative 11 over 2 minus 5t, z equals 0, which I don't need to show, plus 2t, so z equals 2t. So I forgot that when I read this, find the intersection, I remembered that we highlighted parametrics above. So once you have the vector equation, it's easy to get the parametrics. Okay, so our last question. Find the intersection of these two planes if it exists. So the normal of the first one is 2, negative 1, 1. And the normal of the second one is 4, negative 1, negative 1. So they're not scalar multiples. So that means automatically we have a line of intersection. So we want to find the direction vector of that line of intersection first by finding the cross product. I've got lots of room on this page, so I'll go ahead and do my cross product over here. So it's going to be positive 1 minus negative 1. 4 minus negative 2. And negative 2 minus negative 4, which is 2, 6, 2. So my direction vector is going to be 1, 3, 1. So there's my direction. Now we want to find a shared point. Now we can let z equal 0, and we would end up with our equation 1 being 2x minus y equals 5 if we rearrange it, and our second being 4x minus y equals negative 1 if we arrange it. And we can eliminate y by subtracting. So we're going to subtract here. So if we do that, 2x minus 4x is negative 2x. Negative y subtract negative y is 0. 5 minus negative 1 is 6. So we end up getting x equal to negative 3. So we've got our z and our x, so we have to find y. That goes with x being negative 3 and z being 0. So I'm going to use the first equation here. 2x minus y equals 5. 2 times negative 3 minus y equals 5. So if I add y over here and subtract 5 over there, I get negative 11. So then I'm going to check, is the point x being negative 3, y being negative 11, z being 0 on both planes? So I'm going to do a left side, right side check for each plane. So my first plane, 2x minus y plus z minus 5 equals 0. And I'm testing the point where x is negative 3, y is negative 11, Z is 0. And I do get 0, so therefore P is on pi 1 because the left side equals the right side. And then I'm also going to do the same thing for the second plane, which is 4x minus y minus z plus 1 equals 0, where x is -3, y is -11, z is 0. And again, I get 0, so therefore left side equals right side. Therefore, P is also on pi 2. So we know that this is a shared point. It's on both planes, so it has to be on the line of intersection. We know this is the direction of the line of intersection. So then we can, it doesn't specify how to write it, so I always use a vector if it doesn't say that. So therefore, LOI is R equals -3, -11, 0, plus my parameter t times the direction vector 1, 3, 1. Okay, so and then success criteria, you can analyze the normals of the two planes to decide between parallel and distinct, which would mean no intersection or coincident, a plane of intersection, or do we have a line of intersection? So are the normals scalar multiples or are they not? And you can find the line of intersection of two planes that intersect in a line by first finding the direction vector, which is going to be the cross product of the normals, and then finding a point shared by both planes. And then usually you put the line of intersection in vector form, state it in vector form, but we did have that one question where we had to put it in parametrics. Okay.